Now, this is the first video on Chapter 6. I'm going to go over the first three sections with you. So Section 1 is on properties of gases. So this is the kinetic molecular theory that describes some of the properties that gases have in common. So the first one, gases move rapidly in straight lines. A real gas doesn't do that necessarily. It might bend towards the others. They have essentially no attractive forces. Again, a real gas might have a little bit of an attractive force. But what is true is that gas molecules are always pretty far apart. They have very small volumes compared to the container, and their speed, their kinetic energies, will increase if the temperature goes up. We're going to describe gases in terms of four properties: pressure, volume, temperature, and how much of the gas we have. Now for pressure, we're going to use different units, and we're going to see those coming up. You can see them listed here on the right. For volume, we can have milliliters or liters. That's usually what we'll see. Now for temperature, we're going to have Kelvin in any of the calculations that we do. So you got to remember how to get Kelvin from centigrade. And for the amount, when we get to that, we're probably going to use moles. Now let's check out the four properties. So first property is pressure. Now gas particles are small, have a lot of energy, and they can create pressure if they're in a container when they smash into the side of a container. So that's one way a gas creates pressure. Now, gases in the air create pressure because of their weight, and that's what this diagram here is showing you. All this mass of air is pressing down on this person, and that's creating pressure on that person. So that's atmospheric pressure, which is different from the pressure that a gas in a container creates. The volume of the gas is going to be whatever the volume of the container is. A gas always expands to fill up that container because it's moving so rapidly, it gets every place pretty much at the same time. If the number of collisions increases on the sides of the container, the pressure is going to go up. Or if the gas particles move faster, then they'll hit the side of the container harder, and that'll increase the pressure as well. Now temperature we're going to measure the temperature in Kelvin, and the temperature gives us an idea about what the average kinetic energy is. Now it doesn't tell us what it is exactly, but we know that if the temperature is higher in one container than another, then the gas in the first container would have more kinetic energy. So the higher the temperature, the higher the kinetic energy. All right, now section 2, we're going to concentrate here on gas pressure. And in the picture that we have, we can see that they're talking about an atmosphere. There's a pressure unit, and they're showing that on top of a mountain, there's less air above you, so the pressure is less. And at the sea level, since there's more air above you from sea level to the outer reaches of the atmosphere, the pressure is greater. So pressure, in a physics definition, is the force per unit area, and the force is usually considered to be a mass. Now here are some of the units of pressure. The largest unit is called an atmosphere, which we're going to abbreviate as ATM. We also have millimeters of mercury. We have torrs, in honor of Torricelli, who invented the barometer. In this country, we still use pounds per square inch, and we have kilopascals that we use in the international system. So the units that you're going to see in problems are probably going to be more like the first two. Now you notice that all of these units equal 1 atmosphere, which means they also equal each other. So we're going to be using some of these conversions. Now here we have a table of altitude versus atmospheric pressure. So what you want to notice is that at sea level, we're saying the altitude is 0 here. That's our pressure. That's called standard pressure, 760 millimeters of mercury. If you're below sea level, like at the Dead Sea, you have higher pressure because there's more air above you. Now here we start to go to higher and higher altitudes. So Los Angeles is a little bit above sea level. You see the pressure is less. Look at Denver, mile-high city, pressure is a lot less. Mount Everest, where you're very high altitude, pressure is quite a bit less than it was originally. It's only about a third now of what it was at sea level. So let's see if you can answer these two questions. And this is just about, can you make some conversions? So it says, what is 475 millimeters of mercury in atmospheres? And the second one, if you have 2 atmospheres of pressure, what's that in millimeters of mercury? Kind of going backwards with it. So you have to know what the conversion factor is to do this. Now the conversion factor you can find in the previous slide. Now I can also write it in here. The conversion factor is 1 ATM equals 760 millimeters of mercury. We'll see where that came from later. So using this conversion factor, and why don't you try to solve the problems, and then you come back, check the next slide, and you'll see the solution. Okay, here's the solution. So we start off with the problem, what's 475 millimeters of mercury in atmospheres, and we want to set up our solution so we can cancel out the millimeters of mercury. That's the conversion factor, and here's our answer. You notice 3 significant figures just like we started with. And the second problem, we're starting with 2 atmospheres, that's 3 significant figures, and we're multiplying it by the conversion factor, so the atmospheres will cancel, and then we still get 3 significant figures for our answer. So that's consistent. A barometer is a device that was invented by Torricelli back in the 1600s, and it's used to measure air pressure. And it kind of works like this. We have a large tube, probably about a couple of feet long, and it was filled with mercury, and then it was tipped upside down where the mouth of the tube then is placed under the level of mercury in this pan. Most of the mercury stays in the tube like this. Now what's keeping the mercury in the tube is actually the weight of the air pressing down on the surface of the mercury in the pan. The only way the mercury can go is up the tube. Now gravity is trying to pull it down. So we have 2 opposing forces here. Atmospheric pressure, or the weight of the air pushing the mercury up, and gravity pulling it down. Now gravity doesn't change much no matter where you are on this planet, but air pressure does. So if the air pressure becomes less, then the mercury will start to come out of the tube. So the first pressure unit that we had is really the height of the mercury in the tube, and that's why you get this funny looking unit, millimeters of mercury. Now I mentioned this at the beginning of the slideshow. As far as altitude goes, the higher you are, so we're up on top of a mountain, the lower the air pressure. And so at sea level, we have 1 atmosphere pressure. Again, it's called standard pressure. And on high elevation, we have much less than that. And this affects the boiling points of liquids. All right, here's a couple of questions for you to answer. The downward pressure of the mercury in a barometer is, what do you think, greater than, less than, or the same as the pressure of the atmosphere? And 2, a water barometer is 13.6 times taller than a mercury barometer. Here's the density of mercury, because, and what do you think the right answer is? All right, here are the answers. For number 1, the answer is C. The downward pressure of mercury in a barometer is greater than the pressure of the atmosphere. And number 2, a water barometer is 13.6 times taller than a mercury barometer. And that's because water is less dense than mercury. All right, this is the last section that we're going to go over in this slideshow. Pressure and volume. And it's going to give us Boyle's law, which is involved in breathing. And that's why you see that diagram there. So we start off with Boyle's law. We take a look at this piston cylinder setup. We start off with a piston in the cylinder. We have a gas inside the cylinder. Gas particles are bouncing all over the walls of the container. When they do that, they create pressure, and they create enough pressure to keep the piston up this high. Now at this point in time, the volume is 4 liters, and the pressure that's exerted inside the container is 1 atmosphere. So the question is, what will happen if I were to increase the pressure? What if I could put a weight that would push down on the surface here of the piston that would squeeze those particles closer together? So see what happens when I do that, the pressure goes up. So when I cut the volume in half, the pressure doubled. Now how come the pressure went up? Well, the difference between these 2 situations is now in the second container, the gas particles have much shorter distance to travel between collisions. Therefore, the number of collisions goes up, and that's what makes the pressure go up. Now we want to be able to actually calculate what maybe a new volume would be or what a new pressure would be when we make these changes. And so to do that, we're going to be using Boyle's law, which you see written down here. So here's Boyle's law, and just to show you how that works, P1, V1, now the 1s mean the original conditions and the 2s mean the final conditions. So here they're giving you an example. If we started with 8 atmospheres and we had a volume of 2 liters, so if you multiply those 2 together, you get 16 atmosphere liters. Now, P2V2, a second set of conditions, what if the pressure was cut in half? Well, if the pressure went down by half, the volume then would double. But notice that when you multiply the numbers together, you still get the same value. And we can do the same thing here for pressure and volume number 3. So again, this is Boyle's law. P1V1 equals P2V2. And that means when the temperature isn't changing and the amount of the gas is also not changing. Now, when you inhale, this is going to be an application of Boyle's law. So we know that when we inhale, we're trying to get the air to come into our mouth and our nose to come down into our lungs. Now, air isn't like a liquid or a solid that we can actually, drink or eat. So how do we get the air to come into our lungs? We have to create a situation in our lungs where the pressure is low. So therefore, because the pressure outside would be greater, the air comes into our lungs. So how do we make the pressure inside our lungs become less? We make the volume become bigger. And that's what happens on inhalation. The lungs expand and the pressure goes down, and then air will come in. And then the opposite happens when you exhale. So when you exhale, the muscles relax and the lungs, they shrink up so the pressure goes up, and then that forces the air out. So how easy or harder it is to breathe sometimes is a factor of what's the air pressure outside of you. Now we're going to be using Boyle's law to solve some simple problems. So we start off with Boyle's law, and let's say we wanted to solve it for V2. What would that was unknown? If we're trying to find V2, we start off with our problem here, with our Boyle's law, You notice V2 is next to P2. And I say I have to get rid of the P2. So I would divide both sides by P2. And then the P2 would cancel out over here. And then I'd wind up with P1V1 over P2 equals V2. And then I can just plug my values in. As long as my pressures have the same units, this will work. So we have our barometer again here, and I have no idea why they put it back in here, so I'm going to go right by it. And I'm going to write by that again. Okay, using the guide to using the gas laws. So these are the steps that we're going to go through. Organize your data. We're going to make a little chart for that. We're going to rearrange the gas law equation to solve for our unknown. And then we're going to substitute our values in. And that should work pretty well. So let's try the first problem. So here we have Freon. This is a refrigerant. It's a liquid in part of the refrigerator and turns into a gas in the freezer. And they say, what is the new volume of an 8-liter sample of Freon gas? So we're looking for volume. If the Freon gas was initially at 550 millimeters of mercury, after its pressure changed to 220 millimeters at constant temperature in moles. Now, reading this, it can be hard to figure out what do they really give me. So what I want to do is make up a little table. I'm going to list things and label them as P1, V1, P2, V2. So if we read this again, the 550 millimeters of mercury was it says initially here, that's going to give me my P1. And my initial volume was 8 liters. That's why I put them together here. My final pressure is 220 millimeters of mercury, and I'm looking for V2. So I've got to keep that in mind. So V2 is my unknown. So I write down my gas law first, Boyle's law, and then I'm going to solve it for V2. Remember, that means I got to divide P2 out of there, and then I wind up with this. Now, when I set up my solution, notice I cancel out my units, and I get the volume becoming 2 liters from 8 liters. Now, a good way to check it is that you notice on the data that the pressure went up. So if the pressure goes up, it went from 550 to 220 millimeters of mercury. If the pressure goes up, the volume will go down. And that's exactly what we have happening. Went from 8 liters down to 2 liters. Now here's a problem for you to try. And see, go through the whole thing, write down the data first, and then take your gas law and solve it for your unknown. So we start off with a sample of oxygen gas at a volume of 12 liters, so that's going to be V1. At 600 millimeters of mercury, that's going to be P1. What's the new pressure? That's your unknown. And 36.0 liters is your V2. So let's see if you can solve this one. So pause the video and come on back then and you can see the solution. Okay, here we go. So we have our problem, and we want to organize our data. So that's what I've done, as I mentioned earlier. So you notice now we want P2. So when I write down Boyle's law, I'm going to solve it for P2. So in order to get P2, I have to get V2 out of there. So remember, originally V2 was over here. Right, so I have to divide that out. So this is my formula now. And then when I plug in my values, my liters will cancel, and I get 200 millimeters of mercury for an answer. Now let's make sure that this makes sense. So what happened? Our volume went up, so our pressure must have gone down. And our volume went up 3 times, so pressure went down 3 times. Let's get ready to check it. So here's another one for you to answer. This just doesn't involve any math. So for a cylinder containing helium gas, indicate if cylinder A or B represents the new volume for the following changes. So we're starting off here. This is our initial volume. And number 1 says, what if the pressure goes down? So if the pressure inside here goes down, actually they mean the pressure on top. If the pressure on top goes down, which one of these will be the result? And then for number 2, if the pressure on top is increased, which one of these will be the result? So what do you think the answers are? So write down your answers and then let's check it. Yeah, if the pressure decreases, and again that's a downward pressure, if the pressure goes down, then the volume is going to go up. And then for number 2, if the pressure is increased, then the volume goes down. So increasing the pressure decreases the volume. Now here's another problem for you to try. If a sample of helium gas has a volume of 120 milliliters and a pressure of 850 millimeters of mercury, what's the new volume if the pressure is changed to 425? So we have 120 milliliters, that's my V1. 850 millimeters of mercury is my P1. They want the new pressure, or they want the new volume, that's V2 is the unknown, and this is P2. So what I want to do is make up a little chart with that to see where I am. And here's my chart. And so I'm going to solve Boyle's law for V2. Now when I do, I wind up getting this. And then I just have to plug in my data. So if I plug in my data, my millimeters of mercury will cancel, and I get 240 millimeters for an answer. So you notice that if you look back at the problem, the volume is what we want to figure out. But let's see what's happening to the pressure. If the pressure goes down, the volume has to go up. In this, the pressure is being cut in half. So if the pressure is being cut in half, the volume has to double. And that's exactly what happened. 240 is exactly 2 times 120. So you should be able to figure out what your answer should be before you actually do the problem. Okay, another learning check. I think this is the last one now. A sample of helium gas in a balloon has a volume of 6.4 liters at a pressure of 0.70 atmospheres. At 1.40 atmospheres. So if the pressure goes up, what will be the new volume of the gas? Will it be A, B, or C? So you're starting here, and you're going to double the pressure on the balloon. Right? Sample gas in a balloon. Oh, okay. Well, let's see what will happen. Aha! It'll go down, so I was right. They're not talking about the pressure inside the balloon going up. They mean the pressure outside going up, and that's why the balloon got smaller. Sometimes the questions can be a little tricky. Okay, and that is the end of the show.